Under the vast heavens above, a colossal crimson star, one of the brightest and most easily identifiable among stellar bodies, dominates the horizon. It exists far beyond the reach of our complete comprehension. This colossal cosmic object has the potential to release energy so immense that it could rival the collective brightness of countless stars. This astronomical behemoth, possibly on the brink of a cataclysmic event, might soon erupt with such force that its glow could surpass the combined brilliance of 1 billion suns. The crucial question, however, is whether humanity is prepared for the consequences of such an event. This giant red star, often called Goliath, lies relatively close to Earth, and it has become a topic of intense interest and debate within both the scientific community and the general public. Recently, the star underwent a significant transformation that has raised alarms and sparked intense discussions about its future trajectory. The most concerning possibility is that this change could indicate the early signs of a supernova, an explosive event marking the final phase of a star's life cycle. If Alpha Orionis, this star's scientific designation, were to run out of nuclear fuel, it might collapse under its own gravitational force, triggering a catastrophic explosion. The very notion of such an event causes concern not only for scientists, but also for those of us on Earth, as its potential aftermath could be extraordinary. Alpha Orionis, easily identified by its rich crimson hue, holds the distinction of being the largest and brightest star in the Orion constellation. Using advanced tools like NASA's Hubble Space Telescope, astronomers have closely monitored its behavior, especially in 2019 when it experienced a significant loss of mass, a rare phenomenon for stars of its type, which has raised alarms in the scientific community. While our Sun often experiences coronal mass ejections, the unusual events seen in Alpha Orionis have prompted a reassessment of what occurs during the final stages of a massive star's life. Scientists are divided on the exact distance of Alpha Orionis from Earth, with some placing it as far as 1,200 light-years away, while others suggest it might be as close as 724 light-years. The challenge in determining its precise location stems from the vast distances involved and the unique nature of red giants. Despite uncertainties about its exact position, Alpha Orionis continues to captivate astronomers, remaining one of the most awe-inspiring objects in the night sky, shining several times brighter than our Sun. However, this intense glow comes at a considerable cost, as Alpha Orionis is consuming its nuclear fuel at an accelerated rate, speeding its journey toward the inevitable conclusion of its life cycle. Once it depletes its fuel supply, the star will likely collapse, potentially forming either a neutron star or, in a more catastrophic scenario, a black hole, depending on the nature of the explosion. This raises an important question. Could Alpha Orionis pose a threat to Earth? If a supernova were to occur within just a few light-years of our planet, the consequences would be devastating. A supernova can release an unimaginable amount of energy, potentially outshining entire galaxies. Even if Alpha Orionis lies at a considerable distance from Earth, the implications could still be far-reaching. The last supernova event recorded within our galaxy occurred in 1604, and since then, humanity has not witnessed a similar occurrence on a local scale. However, a significant supernova did explode in 1987 in the Large Magellanic Cloud, located 169,000 light-years away. While this explosion had substantial effects on its immediate surroundings, it posed no direct threat to Earth. Still, these rare events serve as stark reminders of the immense scale of supernova explosions and the potential dangers they pose. A supernova, especially one occurring near Earth, could create a danger zone surrounding the stellar explosion. The risks to life on Earth should be considered in the broader context of cosmic events. While supernovae are relatively infrequent, gamma-ray bursts, GRBs, represent an even greater threat. These bursts can obliterate entire planetary biospheres, bombarding them with deadly radiation. For example, GRBs have the potential to destroy a planet's ozone layer, leaving it vulnerable to harmful ultraviolet radiation from its star, effects that could persist long after the burst has subsided. This looming threat of GRBs has become a focal point for current research, shedding new light on the potential hazards of stellar explosions that result in such catastrophic events. When massive stars explode as supernovae, their brightness can exceed that of entire galaxies. This intensity raises a critical question: what would happen if Alpha Orionis were to undergo a similar transformation? If it were to explode as a supernova, it could become the second brightest object in the sky after the Sun in terms of visibility. Even at a considerable distance, the energy released in such an explosion might be so intense that it could be visible during daylight hours. This dazzling spectacle would cast shadows at midday, offering a striking yet unsettling experience for those witnessing it. While the visible light emitted by a supernova would undoubtedly be a captivating sight, the real threat lies in the high-energy radiation accompanying such an explosion. This radiation, usually in the form of X-rays and gamma rays, could have far-reaching consequences. One of the primary concerns: its potential to deplete Earth's protective ozone layer is a major concern. Without the ozone layer, life on Earth would be exposed to harmful levels of ultraviolet radiation, potentially leading to extinction events. The dangers posed by a supernova do not dissipate immediately after the explosion. The remnants of the explosion, including shock waves traveling nearly at the speed of light, would continue to pose threats as they propagate throughout the solar system. These shock waves could cause further damage to the ozone layer, subjecting Earth to an even greater risk of harmful radiation, which would only increase over time. Moreover, the long-term effects of the energy released by a supernova could persist for centuries, leaving lasting damage to the planet. Interestingly, some studies suggest that Earth may have already been impacted by the aftermath of a supernova in the past. Elevated levels of iron-60, a radioactive isotope produced during supernova explosions, have been found in deep-sea sediments and lunar soil, suggesting that Earth has likely encountered the fallout from such an event in its geological history, possibly within the last few million years. At present, no known supernova candidates pose an immediate threat to Earth. However, ongoing research continues to uncover new potential dangers, especially from supernovae capable of emitting long-range lethal radiation. These supernovae occur when a star nearing the end of its life is surrounded by a massive disk of material, and the shock waves from the explosion interact with this material, creating intense X-ray radiation that can travel vast distances through space. This radiation has the potential to affect planets within a 150 light-year radius. Fortunately, no such candidates have been identified near Earth. Nonetheless, this research has provided new insights into the concept of the habitable zone, the region of space where conditions might support life. It appears that this zone may be more restricted than previously thought, with the outer regions of galaxies lacking sufficient star formation to support the development of rocky planets. On the other hand, the inner regions, where stars are born and die more rapidly, may pose risks due to the frequent occurrence of supernovae. As scientists continue to investigate the remnants of supernovae, they are discovering that these cosmic leftovers can give rise to new stars, forming stellar nurseries from the material ejected during the explosion. This process highlights the interconnectedness of the universe, where the death of one star often leads to the birth of another. Furthermore, supernovae have proven to be invaluable tools for measuring cosmic distances. Type Ia supernovae, in particular, are used as standard candles, allowing astronomers to measure distances between galaxies with remarkable precision. This method has refined our understanding of the universe's vastness and provided vital information about dark energy and the accelerating expansion of the cosmos. The remnants of supernovae, consisting of the material expelled during the explosion, play a crucial role in the formation of new stars. These remnants serve as stellar nurseries, where fresh stars are born from the gas and dust left behind. This cyclical process, where the death of a massive star leads to the creation of new generations of stars, drives the evolution of galaxies and contributes to the ever-changing structure of the universe. As astronomers continue to study supernova remnants, they are finding that new stars can emerge from the gas and dust in these regions, even years after the initial explosion. Supernova remnants, with their complex compositions, are also one of the universe's primary sources of heavy elements. Elements such as iron, gold, silver, and uranium are formed in the extreme conditions of a supernova explosion, and they are scattered into the interstellar medium, enriching the matter that will eventually form new stars, planets, and even life itself. Without these heavy elements, the solar system and indeed our existence would not be possible. Supernovae, therefore, are not merely destructive events. They also play a vital role in the creation of the very elements that make up the stars and planets we observe today. Furthermore, the study of supernovae has deepened our understanding of the universe's expansion. By observing the brightness of type Ia supernovae caused by the explosion of a white dwarf in a binary system, astronomers can measure cosmic distances with extraordinary accuracy. These standard candles have revolutionized our ability to map the universe, providing crucial information about dark energy and the accelerating expansion of space. Despite the significant advancements in our ability to measure cosmic distances, the potential dangers posed by supernovae cannot be ignored. While the likelihood of a nearby supernova affecting Earth remains low, the long-term consequences of such an explosion could be profound. As mentioned earlier, supernovae emit intense radiation that could disrupt the solar system's environment. This radiation could interact with Earth's atmosphere, depleting the ozone layer and exposing life to harmful ultraviolet radiation from the sun. Without the ozone layer, survival on Earth could become increasingly difficult, if not impossible. Additionally, the shock waves from a nearby supernova could disrupt the structure of the solar system.